Hi, I'm Alvaro. Welcome to the Unnamed Reverse Engineering Podcast, where my co-host Jen and I sacrifice our victims.
And who's our victim today?
Yeah, exactly.
Hi, everybody.
So I'm just going to go with it. Hello, everyone. Welcome to the Unnamed Reverse Engineering Podcast. I'm Alvaro.
And I'm Jen.
And welcome to our guest. Can you tell us who you are?
Yeah, I'm really excited to find out.
Hi, I'm Tube Time, and you can call me Eric. I'm a hardware hacker into reverse engineering and forward engineering as well. And I've had a couple of notable projects, including the world's largest 6502 microprocessor called the Monster 6502. And I've also reverse engineered the original Sound Blaster sound card and cloned it. And I've done the same thing to a couple of other cards as well.
Welcome.
Welcome. I have one first question. When you reverse engineered the Sound Blaster, was it in the 90s?
It was not in the 90s. It was very
Am I
recently.
close?
Just a couple of years ago. But the sound card itself was the original version from 1989.
Oh,
so it came out quite a long time
16?
ago, but before that. So this is a Sound Blaster 1.0, and Creative Labs came out with this product. I think it was one of their first few products. They had one sound card before then, but just it never really did well in the market. But what they did with the Sound Blaster is they combined ad-lib synthesizer functionality. Ad-lib was an older sound card that was pretty well accepted and used by a lot of different games at the time. And they combined it with digital audio playback and recording and a joystick, which was really important because if you wanted a joystick on your computer, you had to spend $40 in late 80s dollars to get a special card just for the joystick interface.
yeah. I remember what Jen mentioned, the Sound Blaster 16, but that was early to mid 90s, I think, right?
Yeah.
And yeah, it came with a
Sound Blaster
CD-ROM.
16. Yeah, that was a couple years later.
Yeah.
This was in the time period when I can't remember what the cost was quite at the time. It's either $25 or $100 for 1 meg of RAM in that time period.
Yeah, it was an expensive card too. I think it was $200 or something like that. Don't quote me on that. You'll have to go do your own Google search.
It feels like 100 to 200. Yeah,
Cheaper than you can get them now on eBay, right?
I know.
Really?
Yeah, eBay prices for those really spiked high, which was one of the reasons I did this project in the first place. Because I had a card back in the day, but it got thrown out with the rest of the EWaste at some point in the early 2000s. And then I thought, well, I want to have this card so I can put it into some of my retro gaming machines or whatever. But, eBay, they were just really, really expensive. So that's when I decided to reverse engineer it.
So you're saying I threw out a bunch of stuff out of my dad's house that could have been worth something.
I know, that's the thing. But at the time when you do it, it's just junk, right? I mean, it's
it's exhausting.
or whatever.
You're just like, just get rid of it. I don't have time to deal with it.
And then 20 years later, you're like, oh, man, I want to relive those moments.
Oh, wait, this wasn't 20 years ago. So this was like 3 years ago.
Well, no, but the original one was a little bit longer.
Right.
But I'm talking about when I'm throwing it out.
Oh, yeah.
There is one part of that reverse engineering challenge, which I kind of forgot to mention. And remember, I couldn't get a card. So I didn't have a physical card anymore. But I'm trying to reverse engineer this thing. And I was able to do it entirely from pictures. So somebody on the internet had put up a photo of the front and the back, and that was it. The back isn't that hard because there's no parts on it, and you can follow the traces. It's just a 2-layer board. It's not that bad. The front gets trickier because there are components in the way. There are traces that run underneath the dip chips and stuff like that, and you can't really see where they go. And so I found somebody on Twitter who had an actual card, and they were fully equipped with rework equipment. And they were able to remove a couple of chips and then take a few photos of what it looked like underneath those chips. And then I used that information to sort of figure out where those traces went, what the layout looked like, and all of that.
Yeah. So in that case, you're saying, were these socketed or were these just directly soldered through hole dip chips?
They were directly soldered onto the board. So this guy had to go through with a desoldering gun and remove, probably 100, 150, 200 solder joints to get these parts out on a, somewhat rare card. I mean, I don't really consider it to be all that rare, but let's just say it's an expensive card.
Yeah.
So I am very, very grateful for him for doing that, because I really wouldn't have gotten that far.
Was this your hardware IO talk? Was this the one that was on, or is this a different one? Because I know you've done a few.
Yes. So all the gory details you can find in the hardware.io talk.
Okay, cool.
That was 2 years ago?
A couple of years ago now,
Yeah.
Doesn't feel like it.
So technology-wise, though, given we're talking late 80s, maybe early 90s, like the traces are obviously pretty thick, and it's a two-layer board.
I think they're like 10 mil traces, and they're not all that tightly spaced. Mm-hmm. And the process is basically you snap a couple of pictures, or you find a couple of pictures on the internet that are hopefully high resolution enough. And then one of my tricks is to look at the chips. And since the chips are these old DIP ICs, you know that the pin-to-pin spacing is 100 mils. And based on that, you can figure out the scale factor of the image.
Oh, for the photo. Okay.
Right. Because the whole point is to reverse engineer the layout as well. If you want to do a really thorough clone, you have to know what all the dimensions are. But if you don't have a physical card, you can't just measure it directly. And so the trick is to take a couple of measurements off of the pin-to-pin spacing. And then from that, you can kind of average it out and figure out what your dots per inch looks like on those images. And then from there, it's just a matter of tracing over it and then figuring out what all the parts are on the board. With a DIP chip, it's not that hard because they all have a full part number on the top. With a modern device, like some of those little tiny surface mount chips, all they really have room for is a top mark. And that makes things far more difficult.
And are getting the components on the board, is that hard nowadays? Ignoring the supply chain issues, I figure these
what do you mean?
Hopefully not affected. But
what do you mean getting them on the board?
No, like getting the components. Like you can clone the PCB, but you still have to get some of the chips that might not be as common.
Oh, I see what you're saying. A lot of the older parts, they wind up as e-waste ultimately, right? Like we all had computers and cards and stuff back in the old days. And when we throw them into e-waste, they get shipped to a recycling facility, often out here. Often they would get shipped overseas into China. And what they do then is they desolder all those chips. So they have like a solder pot and hot air and all kinds of, sometimes even just literally a fire, like fire with like coal or wood or whatever. And so they just remove the chips and they clean the leads. So they clean all the solder off the leads and they sort them. And once they're sorted, they throw them into tubes and those get sent off to brokers. And what that means now is we actually can go and at China, we can buy these parts back that were originally e-waste and sent to China. We can buy them back. Now, of course, we're going to spend a lot more money, but they're still available, at least to a degree. So certain devices like the Yamaha synthesizer chips are getting harder and harder to find because there are just so many projects now, open source projects or whatever, that use those devices. But for the most part, you could just go there and find a lot of these old chips.
Is that how we're supposed to understand? So I know that there's scavenging, particularly like I've seen this done, like if you're in a startup and you need to scrap a bunch of boards for whatever reason, you can then salvage those parts and either put them back into your line, or you can then sell them and see if any brokers will pick them up. So in a startup, I know I've done that. What's interesting with these is I'm suspecting that if I'm in Shenzhen and I go down to the markets there and I'm on the bottom floor, that's where those chips are, in the tubes, those older ones, because I think those are where those vendors are. I don't think they're up in the upper floors, but I think that's where I've seen exactly what you're describing there.
Yeah, and I think that's especially relevant nowadays with the horrible part shortage that we're going through.
Yeah.
In fact, a lot of contract manufacturers, they do this thing as a service now. They call it cannibalism. You ship them a bunch of boards and they'll pull off whatever parts you want to use for your new build.
Does CM start doing this
crazy,
like
but
officially?
we've gotten to that point. Yeah. It's a real thing.
Might have to do that.
I haven't done it yet, but I have a feeling I'm going to have to be doing that in the future.
Yeah. No, Some of the parts that used to be $8 to now $80. It's like, oh, maybe it's worth
Really?
Oh yeah,
I
STM32.
didn't
Definitely.
realize it had gotten that bad.
I just tweeted earlier about the STM32. If you go on DigiKey and you look at just the STM32 microcontroller, there's something like 3,000 and change different part numbers. And then when you click that little checkbox that says in stock, that number goes down to 29 or whatever it is. It's probably going to be even lower by the time this airs.
Yeah.
Which series are they in that case?
Everything. Oh, you mean the 29?
Of the ones that are available, is it F series? Is it?
I don't remember.
Know?
There are more difficult parts to use, like some of the BGA devices and some of the more obscure variants, but all the common stuff is just completely cleaned out.
Wow.
Yeah, no, it's incredible.
I feel very sheltered at the moment. I won't deny that.
It is a little discouraging. At the same time, if I'm building retro recreations,
this is great.
I'm using older chips, and it's not really that much of a problem. I mean, it's no different than it's been before, because a lot of these chips you can't really buy brand new anymore because they come in dip, and
nobody's
honestly,
hoarding
very
them
few companies
because
do that.
they need to do a build.
Yeah. Okay. Well, that said, like, let's say you do buy something from China, some retro chip from China that you need to fill out or fix something. How long is it taking to arrive? Is it really worth
it takes about a month, but I haven't done that in a while. So
yeah, I was gonna say, I think I heard there's like a big shipping issue at the moment, so that's why I was asking.
Oh, if it comes via boat, yeah, I can tell you that.
Yeah, if it takes the boat, it's going to be a lot longer.
Yeah,
but I haven't bought one of those chips in at least 6 months. You can buy pretty much whatever you want from if you find the right broker. The issue is you may pay a lot of money depending on what it is.
Yeah.
And you also have to expect at least one of them not to work. And so I usually buy multiples and say, well, if I buy 5 of them and 2 of them work, then I'm good to go.
Do any of these vendors guarantee that they will work?
Oh, no. It's all, I mean, this is gray market stuff we're talking about. So they know. And as the buyer, I know.
It's an understanding.
Is there any possibility that you might get a fake one?
And it's happened to me before.
Oh, really?
Quite frequently. Yeah. What they typically do, and it's not like I haven't really run into a situation very often where it's a different part that's been relabeled. So it's not the part that it claims to be. Typically, it actually is the correct part. But what they've done is they've freshened up the date code, which is actually kind of hilarious because I bought some sound chips probably last year, and they had date codes from like 2015, which is hilarious because these parts were discontinued in like 1999.
End of life.
Got the freshest.
So I'm looking at those date codes and I'm like, and looking at the surface of the chip. And
I
I'm
guess
thinking,
the question is like, what exactly counts as freshening something up?
Little sprinkles.
What you do is you plate the leads. So you fix the plating on the leads, make it look like it's a fresh new part, fresh off the factory line. Then you blacktop it. So you basically sand it down a little bit. You paint the top. And they have paint now that you can't really dissolve in isopropyl alcohol, although there are other solvents that will dissolve it. And then they laser mark, or sometimes they'll paint the new number on top with a silk screening process. And so you look at it and you go, oh, wow, this part looks fresh and new. It must have been new old stock in storage somewhere. The answer is no. This was actually pulled off of a circuit board, but then it's been freshened up and given a new coat of paint and made to look like it's some new thing.
And I know that we're not really talking about reverse engineering here, and we're getting maybe a little of it, but I'm kind of curious about okay, what is the purpose for them to go through that? Is it to get it to be compliant with a lead-free process? Because there's no way that even with the freshening up that is complying with that. So what's the purpose?
The purpose is that for a lot of contract manufacturers, they require that the parts be younger than a certain age to be assembled on a brand new board. So for example, if I send a contract manufacturer some parts that are 5 years old, they're going to look at that. Their incoming QA department is going to look at that and then reject it and say, we're not going to assemble it. And the reason they do that is very practical, because over time, these chips absorb moisture into that sort of matrix of epoxy and glass. And when that happens, and you run it through reflow, or you run it through one of these industrial soldering processes, it will expand rapidly and pop, and can cause damage to neighboring devices, and you're just not going to have a good time.
Now,
and it's
does the
on them.
magic smoke come out at that point, or
Magic steam.
Well, if you power it up, then yes.
it sounds like you don't? This is not even like power on magic smoke. This is just like humidity.
Yeah, this is well
based.
before that. So it'll just crack, or sometimes they actually call it popcorning, where the part will literally jump up into the air and land somewhere else on the board.
It's a little bombed.
Yeah. I wish our audience could see my face. I'm like, ugh.
Yeah. Well, we're not recording your face. Don't worry.
Thank God.
We'll just describe it. No, but we're talking about old parts, and you mentioned earlier, but the Monster 6502, and this is probably your largest project so far, right?
One of my largest projects. Physically the largest.
Yeah.
Physically, is it literally? Yes.
Physically, let's see. Have I done anything more complicated? That's up there. It's up there in one of the most complex projects that I've done. I've done more complicated stuff in for pay circumstances.
Yeah, but stuff that we can see.
Yeah. But for hobby
mortals.
projects, that's probably the most complicated.
Yeah. So tell us about that one.
That was interesting. That was actually based off of a challenge, and my memory's a little fuzzy on this, but from what I understand, this was probably 6 or 7 years ago. It might have even been more than that. And it was a Maker Faire after party, I think.
Bring a hack.
And it might have been Bring a Hack, but somebody came up, and my memory is very fuzzy on this, but somebody else told me that it was actually Bunny Huang who came up and challenged me. He saw the 555 timer that I had built out of discrete components and said something like, well, that's great. You should do a processor. Ha, ha, ha. And at the time I was a little annoyed because I'm like, okay, I mean, I thought this thing was neat. And here's somebody coming along and being like, oh yeah, I see that. And
calling you out. It
stuck in my mind. And I thought about it. And I was talking with some other people. I think I was talking with Wendell about it, of Evil Mad Scientist. And we did this little exercise in what I later found out was essentially Fermi estimation. And the idea is that you just do a calculation based on orders of magnitude. And the idea is, first of all, we want to figure out, is this even possible to do? Like, is it possible to build a microprocessor out of discrete components? Well, I mean, how big is it going to be, right? If it's really, really big, then it's probably not that practical. If it's really small, then obviously it's going to be easy and we should do it. So the question then was, well, how many transistors are there in a typical microprocessor? And we're thinking, well, millions, and then we started thinking, well, what about some of the older processors? Maybe an 8-bit processor or a 4-bit processor. And we settled on a number probably between 5 and 10,000. And then we started talking about, well, how many transistors can you fit, surface mount transistors, can you fit on a circuit board? Mm-hmm. And we're thinking, maybe 4 or 5 in a square centimeter. And so you start to think about it, and then you're like, well, that's not that big. It's not that small. 5,000 isn't really that many, but then you've got that square root working in your favor because it's a big rectangular board. And then you do the math and you wind up with something that's, something that it's a bit larger than a piece of paper, but not too much larger. Mm-hmm. So we sort of looked at each other and we thought, well, this is actually
it's doable.
Practical. This is something that could, in theory, be done.
Yeah.
It probably was as a proto a long time ago.
Yeah, exactly. Yeah, exactly. But I did talk later with the people who designed the 6502, and they told me that was not what they did. They designed it all on paper first, essentially. And I think they built some parts of the circuit, but they didn't really build the whole thing. They were in too much of a hurry.
Did they reach out to you? Like, how did they approach you, or did you approach them?
It was sort of half and half. We became aware of each other over time and met up at a vintage computer festival. So last year we actually got to meet in person. That's Bill Mensch, who was one of the designers of the 6502.
Nice. I miss going to the vintage computer festival. Didn't they have one last? Oh, you're right. You said that last year. This year was the East Coast, right?
Yeah. So I said last year, and I actually meant August.
That's what I'm saying. I'm like, wait a minute. Are you also trying to confuse people with time and space in addition to your identity?
What is time even?
What is time? What is space? I don't know, but I think COVID ruined my sense of time.
Welcome to the club.
I can't smell anything. I can't taste anything. And I also have no idea what time it is.
So
Anyway.
but I do remember you also did prototype individual parts of this thing, right? Like you didn't just
Right.
design and build it.
I kind of went with a backwards approach. Most people, when they're trying to build something, they think about, well, how can I build this thing?
Yeah.
And what circuit do I need to design to do it? And I came into it trying to prove to myself that I couldn't design it. In other words, what's an experiment I can do to prove that this cannot work and I should stop?
Okay.
Right? Because I want to
that
save
is
some
the right
time.
way, in my opinion, by the way.
Well,
Seems
for something
reasonable.
like this.
The quicker you can fail, that means you can now move on to something
To
else.
the next, yeah.
Right. So that's kind of the thinking. And so what I did is I bought a bunch of these parts, like little individual transistors and stuff, and I started building circuits. So I started with some real simple logic gates. And the reason that I did this is that the 6502 uses a type of logic called NMOS. And so it's not CMOS. CMOS stands for complementary metal oxide semiconductors. And it just means that you have a P and an N type transistor that are sort of opposites, logical opposites of each other. NMOS doesn't have that. It's just half of it. It's only the low side drivers. Another way to look at it is imagine an open drain bus like I squared C. So you can drive the line low, but you need a pull up to go high. And that's NMOS. Now, NMOS gets a little bit clever because they have something called a depletion mode pull up. And all that is an NMOS transistor that's been doped in a certain way so that it's stuck on. And when it's stuck on, it acts essentially like a very crude current source, or you could think of it as a nonlinear resistor. Yep. And they do that because resistors on an IC take up tons of room. And you can see that if you look at a microscope photo of a chip, you can see it because it looks like this little serpentine pattern because they just sort of snake them around and fold them back on each other to try and save space. But with the depletion mode load, you don't need to worry about that. It's just a tiny little transistor and you put that in there. And I had never built anything out of NMOS before. I didn't really have any experience with it. And so I bought a couple of chips that had 4 NMOS transistors on one die. And I bought some just regular NMOS power FETs and just started building little logic gates, little NAND gates, NOR gates, that kind of thing. And they're working fine. Then I started building circuits with NMOS transmission gates, and that's where it starts to get interesting.
I have a bunch of questions, but I guess the most immediate one is like, what were you running into? Was it delay glitches? What was it?
At that point, nothing really. It was just getting comfortable with that type of a circuit, just trying to see how fast it could go. You think of I squared C, and I squared C is limited to 400 kilohertz. And perhaps you've done this before, where you've done a board and it's got a really long I squared C bus, where you've got really long wires, and you're wondering why it doesn't work. And so you look at it on an oscilloscope, and then you see that the rise time is super slow, right? So you look at it, and the fall time is great. It's this nice sharp edge, but the rise time is really slow, and that acts as a speed limit for any circuit that uses that approach. Same with NMOS.
I'm really excited to hear what your solution is because I know what we do in semiconductors.
Smaller resistors?
There are tricks, but in NMOS, unfortunately, there's no trick. You're just speed limited. And so what you do is, one way to look at it is that you've got a pull-up resistor, and then you've got parasitic capacitance downstream, which is from the gate input of every FET that you have it connected to. Right. So the more transistors you have connected to the output, the slower it gets because the capacitance goes up. Right. It's gate capacitance times the number of transistors connected to it. So what you can do is you can reduce the fan out. So you could say, well, we're going to limit it to 10 transistors and that's it. If you need to support more transistors than that, then you have to go through some additional buffering. And so then you take a hit on delay, but then you get nice sharp edges that you can use to drive all those gates.
Yeah.
So it's a trade-off. And that's kind of what I was trying to prove out, is that I could do it and I could understand how that whole system worked and how that trade-off worked.
So what adjustments did you make based on your experiments?
Well, the number one thing I found out was that breadboards are slow because they have lots of capacitance. So what I ended up doing was taking little bits of FR4 copper-clad board and soldering the chips to them directly and kind of carving out little circuits that way, just because the parasitic capacitance was slowing everything down. And so that was one adjustment. The other adjustment I made was to change the resistance of the pull-up. And I ended up doing that in the final design in kind of a complicated way, which I'll probably talk about a little bit later.
Mm-hmm.
How did you get the design to begin with, right? Because like, okay, we're saying you're designing a processor, but this processor that existed in IC form, and how did you back out what the transistors were supposed to be?
I did it by the easiest way possible, which is not doing it myself. And
Ooh.
I stood on the shoulders of giants. And so there's this other group of people who took die photos of the 6502 and reverse engineered it and then turned it into a JavaScript simulation. So it's called the Visual 6502 project. And if you haven't looked at that, you should, because it's really, really great.
So what did they find? Like, I guess summarizing this processor, what would be the obvious takeaways? Does it have a very limited instruction set? Does it, like, I guess what's
special about it?
Tell the audience a little bit more about it, just so they have the perspective of it wasn't a Pentium.
Definitely not a Pentium. And in fact, not even a fraction of a Pentium. The 6502, I would say, it wasn't the first 8-bit microprocessor, but it was a very economical and compact 8-bit processor. It's a beautiful design. It's very compact. It's got a very elegant architecture. It uses a very minimal number of transistors, which I found to be very attractive because transistors take up space on a circuit board. And it was very popular in the 70s and 80s, and it formed the heart of very famous computers like the Apple I, the Apple II, and even got used in some game consoles like the Nintendo. So the original Nintendo uses the 6502 IP core in its processor chip.
Did it even have memory inside of it, or it could only access external memory? Like, was it merely just a processor?
Microcontroller versus microprocessor.
It's a microprocessor because it has no onboard peripherals and no onboard memory. It has a handful of registers, but to do anything useful, you have to hook it up to a ROM chip and a RAM chip, and then individual chips for each peripheral. So you might have a UART chip or a GPIO chip. It was the very common approach in the mid 70s, just because the scale of chip integration wasn't that big.
Fair, especially not compared to today. Like, it seems like in the 90s, that's when it really took off, from what I can tell.
Right.
Okay. So, like, going back to the instruction set, how big was the instruction set?
I don't remember the exact number, but it's pretty small.
Like, we're talking less than 100.
Oh yeah, definitely. I mean, it's maybe a couple of dozen instruction mnemonics, and now there are some different addressing modes and all of that. So technically, those are encoded as separate instructions. But what you have to remember isn't a particularly long list.
Okay.
And side question about 6502, you mentioned Nintendo, Apple I, Apple II have these kind of things. Are there a lot of modern tools for reverse engineering 6502 code, like the decompiler, disassembler, that kind of thing?
That's a great question. I don't remember if Ghidra supports it because I haven't used Ghidra to do that. I think the last time I did 6502 code reverse engineering, I must have used a separate disassembler. I don't remember what I used offhand, but it's not particularly tricky. I mean, you could almost look at the machine code and understand it. Like, you look at that and you're like, you see an EA and you're like, oh yeah, that's a no-op. Or you see an A9 and you're like, oh, that's LDA.
It's simple enough to learn it, I guess. Yeah.
Yeah, and a lot of people back in the day memorized it.
Try that with x86.
Yeah, I know, right?
Old x86, you probably could, but not new. Like,
even old x86 was pretty complicated. Variable length instructions and all kinds of addressing modes and quirks. I wouldn't want to do it.
Did you inherit all the quirks from the original design? Like, were all the bugs there, or did you fix any bugs?
I did, and I guess I should continue the story because I built this little prototype program counter because I wanted to prove that it couldn't possibly work. And I figured, well, this program counter has a carry propagation issue. So think of a binary counter. And there's the case where you go from all ones back to 0 again. And what it means is that there's this carry bit that has to propagate from each bit cell to the next bit cell all the way to the top. And it has to do it within one clock cycle. Otherwise, you can't meet timing closure.
Yep.
And so I was kind of worried about that. But as it turns out, it worked okay. And so it was one of those times where I'm looking at it on my bench, and I've got this little proto board, and the program counter's counting. And I'm looking at it thinking, well, dang it, now I have to go and design this whole thing.
I'm kind of curious that, okay, so let's say you are now designing it. You were proved that you couldn't disprove that it couldn't work or that it could work.
Sure.
I'm so confused right now. So what did you do next? How did you go ahead and design this at the transistor level? Were you using kernel maps? Were you just really heavily relying on that virtual 6502? What were you doing?
Right. I started with a Visual 6502 netlist, and it's literally a JS file with a gigantic list of transistors. And there's it's 3,510. And so I turned that into a spreadsheet, and it's a netlist. So it has a transistor, a little designator for it, and then it says the gate connects to this node, and channel 1 connects to this node, channel 2 connects to this node. And some of the nodes have names that are really convenient, like clock and reset and stuff like that. Most of them, they're just a number because the Visual 6502 people didn't know what that net did.
Yeah.
And so with that spreadsheet, I booted up Altium and placed down a transistor and hooked up a little wire to it and put a node name on each pin. And then I marked it off. I highlighted it on the Excel sheet, and then I went to the next one. And I did that for 6 months.
Yeah, that sounds like,
Dedication.
80s, 90s. Like it to me, it sounds like this is approximately what would have happened if you were an engineer during that time. Also, it also sounds like you as an undergrad taking a computer architecture class, this is also what you would be doing.
It's also 6 months of side project, right? Like you were,
yeah,
you had other stuff going on too.
What are you talking about? He quit his other job just to do this. He's like, I'm sorry, I couldn't disprove that I couldn't do it.
Like,
so now I have to do it. So much is riding on this. I'll see you in 6 months.
There were definitely other projects that went on the back burner because of this thing. But basically, I'd go to work all day, and then I'd come home, and in the evenings, I'd just sit in front of Altium for a couple hours and just clicking away on the schematic. And then, of course, when I'm done with the schematic, I've done all this manually, and so it's quite possible I've made mistakes. And I'm looking at it thinking, man, there's got to be a mistake or two in there. How do I prove that there isn't a mistake, or how do I find the mistake in the first place? And as it turns out, it's not that bad because Altium can generate a netlist of its own. So I generated the netlist, and of course, it's in a different format than the original. So I wrote a little crappy Python script, which I do a lot of, and you just went and compared them one to one. Mm-hmm. And sure enough, there were a couple of mistakes, but I managed to catch them early and correct those. So now I have a schematic that looks pretty good. Transistors are where they're supposed to be, and you can kind of figure out what the individual gates do and all of that. Mm-hmm. And then the next task was to turn that into a board layout. And let me tell you, that was another 6 months of tedious Altium clicking around. And
4 layers, right?
Oh, I guess.
Yeah.
Here's the follow-up question. Yeah, here's the follow-up question. What was Wendell doing during this time? Was he occasionally just like, how's it going? And then he just,
Wendell was working on other projects at the time. I mean, at this point, it was all me. And I think he was kind of standing back a little bit, waiting to see what would happen.
Stand back. I have a net list.
It's like, will I ever see Eric again? Will he come out of his cave?
I will say he took some fantastic photos of the thing.
Yeah, Wendell had a lot of design input. So once I had a board that was working, it was looking pretty ugly. And so we had a lot of discussions about how to do certain things. Like, we had lots of discussions about neat little features to add, such as the pads that go all the way around the board. So they're designed to look like the bond pads on the chip, but we figured it would look cool to put them on the circuit board also. And then we also talked about ways to make it actually useful as a microprocessor. And so we added a little ribbon cable connection at the bottom so you can cable it into a 6502 computer. Now, of course, it's not going to work in something like an Apple II because it simply can't go fast enough. So the clock speed does not go up to the 1 megahertz that was capable, or that the original was capable of. It only goes up to about 100 kilohertz or so.
To me, this naturally brings up the question, how did you do validation? Other than the crappy little script that you wrote? How do you...
Validation was tricky. One thing that I was going to mention before was those depletion mode pull-ups. And on the Monster, I used resistors because it's hard to get good depletion mode transistors. There's just a very limited selection of them available. So I just used resistors, but I wrote a Python program to calculate the value of the resistor based on the fan out of the net that it went to. So in other words, I wrote a little program that would traverse the entire tree of nodes in the schematic. And so it would look at every output of a gate and it would say, well, how many inputs are you connected to? Here's the desired propagation delay. And then here's the capacitance, which it could calculate from the number of gates that it was connected to. And then it would solve that for the required resistor value to meet that timing spec.
That's pretty cool.
So it was a little bit of a trick, and it ended up working rather well. But validation's always the hard part. Imagine you're me, and you get a circuit board back, and you open up the package, and it's a really big package, and there's a bunch of packing material in there. You throw all that out of the way. You pull this board out, and it is the biggest board that you've ever held in your life. Okay, for me, that wasn't the case, but it was the biggest board I had held in my life that I had designed myself. And you're looking at it, and it's full of parts, and then you're thinking, how am I going to bring this thing up? Like, what if there's a short circuit on there somewhere? What if I screwed something up? And so I put it on my bench very carefully, anti-static measures, all that stuff, because these boards are also quite expensive.
Yeah.
You know, we're talking in the thousands of dollars.
Current
range.
limits.
So like there's money at stake. And yes, Alvaro, that's the answer. So you use a current limited power supply, and I brought it up really slowly, and I'm watching the current, and I'm looking at it, and it seemed to be okay. And so I started feeding it a clock, and things were happening. By the way, there's LEDs on the board, and the LEDs were blinking and doing things. And so it was looking very promising.
No one died or anything, so that's
No one
good.
died. No one died. So I started experimenting with the clock speed a little bit, slowing it down, speeding it up. And I slowed it down, and then I saw a little tiny puff of smoke. And so I leaped for the power button, shut it off, and I'm looking at the board, and I realize that there's about 4,000 transistors on this board, and I have no idea which ones or one let out the magic smoke. So what do?
Can't you just smell the board?
Thermal camera?
Thermal camera. So I got a thermal camera. I have one of those little Seek thermal cameras.
Yep.
And looked at the board, and I could see that there was this little area that was getting warm. Granted, I flipped on the power supply, but with a lower current limit because I don't want any more smoke coming out of it. And sure enough, there's a spot. And of course, the Seek thermal cameras are pretty low resolution for various reasons, but you look at it, and there's this sort of blobby area in one corner that was getting hot. And I'm looking at it, I think, well, how do I figure this out? How do I figure out which exact transistor is getting hot? And the answer turned out to be Scotch tape.
Oh.
So what I did is I took Scotch tape and I made this sort of little
blanket
array of it. Yeah, blanket of Scotch tape pieces all sort of laid together. Put that on top of the board, flipped on the power, and sure enough, one transistor melted a hole through the Scotch tape.
Wow.
And so
I have a quick question. Why didn't you just put your hand on there instead of like using elaborate crafts?
I don't want to burn myself.
God. Don't you have like kind of like the pads of your fingers like calloused up enough where you can just handle? Okay.
No. I got to maintain the sensitive fingertips for electronics troubleshooting.
But I have built-in resistance now, so.
Yeah, the other trick is you lick your finger. That's something I learned a long time ago. You lick your finger and then you put it on the thing that you think is hot. And if it sizzles, then you pull your finger away very quickly.
You got to be careful though. Like I made the mistake of putting the finger on the thing that was hot, except it was also 400 volts. And then I touched the lead. So it wasn't hot, but it shocked the shit out of me.
Was that the Operation game?
Well, no, that was that SuperCon. No, this was just
a different experience.
400 volt supply for something else. And yeah, the resistors were getting hot earlier. And then I was making sure that they weren't getting hot anymore. And then I touched the wrong thing.
That's a great story you have.
Would not recommend.
Yeah, that's pretty shocking.
Oh, ding, ding, ding.
Like, here you go. I'll chalk up one over here.
You'll have to add a sound effect for that or something.
It's been good so far.
Okay, I'll get on the sound effects.
Yeah.
All right. Well, back to validation.
Yes.
So it turns out, so I pulled the tape up, and strangely enough, the transistor came with it because it got hot enough to melt the solder. It was not a happy transistor.
Well, it saves you the trouble.
It did. And it turns out that what was going on was the fact that
I thought I was going to heaven.
the 6502, yeah, exactly. It was like, nope, I've had enough. Had enough. But the 6502 uses something called dynamic logic, which means that it uses the capacitance on the gate to store state information.
Like
so
a
instead of
register?
using a latch, so instead of
Yeah, I was
using a
going to
latch,
say,
which
did you basically have a flip-flop going there?
well, flip-flops are expensive because they use 6 transistors. But if you use dynamic logic, then you can cheat and use 1 transistor. Well, technically 2, because you need the second one as a transmission gate to basically open and close the connection to the gate of the inverter, which is the second transistor. And what was happening was that the dynamic logic was getting out of a consistent state at a very slow clock speed. And that allowed 2 output drivers, to drive the same line at the same time with opposite states.
Whoops.
And so that's what was getting hot. And so the solution there was to run it at a higher clock speed. And then add some current limiting resistors so that if it did ever somehow get into that state, the resistors would get a little bit warm, but it wouldn't actually damage anything.
That's pretty cool. So you have a upper and lower spec limits, I guess.
Yeah, exactly. And so that was that part of the bring up. The other part was writing a validation suite. And I got lazy and I found some college project online where they had written a 6502 processor validation suite for some sort of a student VHDL project, because I guess they wrote a core in VHDL and they needed a way to test it. And that code was GPL, or not GPL. It was, I think it was MIT license. It was one of the really permissive open source licenses.
Nice.
So I'm like, well, this is great. So I can just go ahead and use it and modify it and then just release any modifications. Like that's perfect. And the next question is, well, how thorough is it? Like, how do I know what kind of test coverage it has? So what I did is I took the Visual 6502 JavaScript and I modified it so that I could run this validation suite on it with a minor change. I could go in through code and break 1 transistor and then run the validation suite to see if it caught that broken transistor. And so I would just then repeat that for every single transistor in the 6502 design. And coverage was about 40%, which wasn't really great.
I was just going to say, you did trust students.
I did trust students, but I did verify it.
Yes.
With
Trust
that
but
program.
verify. That's right.
Trust but verify. So after working on it for a while, I was able to get the coverage up to about 80% or so.
Wow.
And validation is one of those things where we're trying to get beyond 80% is possible, but the effort kind of goes up exponentially. There's always going to be some stupid little transistor that you can't quite get at. So I figured this is probably good enough.
Yeah.
And just, run with that. And so that's essentially how I validated it.
And it worked. Right?
And then it worked. Actually, I was very shocked the first time it ran. It was running BASIC, and I was just looking at it. And you've got 6 months of schematics, 6 months of layout. There's all that accumulated trauma. And here you are, you're staring at this thing, and it works. And there's part of your brain that's telling you, no, this can't be possible. This can't be happening. Just it's working. And I'm just looking at it. And then I started thinking, this is pretty cool.
Hell yeah.
It sounds very cool. I wasn't sure where you were going with that, whether you were upset that it was only running BASIC or whether, wow, it is running BASIC. I
was just happy it wasn't smoking anymore.
I have to say, I'm very intrigued that you completely sidestep the need for the intricacy. Basically, you leveraged the knowledge that was already in the virtual software version to have to escape doing any of the cardinal maps or any of that level of design, and you just basically went with the net list. I feel like that probably also saved
crazy otherwise.
Yeah,
right?
I mean, basically you took a layout class and then a verification, a chip verification class.
Yeah, exactly. I mean, any kind of project that you're approaching, it's sort of the first thing you do is you go out and you look at the literature. You see, well, what's been done so far. Mm-hmm. And if it's something that's open source, maybe it's better to, contribute to that or look at some of the problems that they ran into and just kind of leverage that. I mean, we are all communities, so we should be interacting with each other.
Absolutely.
I agree.
So it was released into the world. Has anyone taken it and Yeah. Has anyone done anything interesting with it?
Well, it hasn't quite been released into the world yet. So Wendell and I are trying to turn it into a thing that you can hopefully buy one of these days. And we're trying to get it going on one of the crowdfunding type campaigns. The problem is that we got hit by this sort of global pandemic, and so that threw a big wrench into things.
When did that happen?
And then I don't know, it was like a few weeks ago, March sometime. And then there was this other like global part shortage thing.
What?
So unfortunately, it's basically on hold.
Both of those things happened? Wait, where was I?
Not on this planet.
I was probably trying to buy toilet paper somewhere and couldn't find any.
Oh yeah. Yeah, so it's been rough.
I see a link. It's called Snappy Video Snapshot. Video movies.
Oh, yes.
What is that?
Snappy Video Snapshot. So imagine it's 1995 and you have a computer.
Okay.
And hackers. So say you've got your VHS tape of Hackers and you're like, I've got this really cool point in the movie that I want to capture as an image file on my PC. How do you do that? Well, there's no such thing as a TV capture card at that point.
No.
But let's say you went out and you bought this little device called a Snappy Video Snapshot, and it plugs into your USB port. No, wait, it doesn't, because USB didn't exist yet.
I thought it did, but it was not widely adopted. It's like you bought. Yeah, I was so sure that we had bought like a Dell computer that had a USB port. But nobody knew what to do with it.
1996.
Oh, okay.
Well, according to Wikipedia.
Okay, then I'm confusing my time.
Is before that.
Okay, so I have my Hackers. I have this. Did I use a parallel port? Did I use a serial port?
You did use a parallel port. So you'd plug it into your parallel port. And for people who've never used the parallel port, they were really great because they were the easiest way to get data in and out of your computer, because it's literally 8 parallel data lines. And it started out, they're unidirectional, so they would only go out of the computer, which was fine because there are 4 status lines that you could use to get information into the computer. And people built all kinds of crazy stuff that plugged into that. I mean, I built a sound card, basically a resistor ladder DAC connected to those 8 outputs. And I could play one of those mod trackers and use it to play mod tunes and stuff like that. It was pretty awesome. So anyway, so the Snappy Video Snapshot was this little device you plug into your parallel port. It had an RCA input on it for video coming in, and you'd hook that up to your VCR. You'd put in your copy of Hackers, you'd play it, you'd hit pause, you would load up the very 90s looking Windows software, and it would show you a live screen of that video. It was live in the sense that it was a few frames per second. It was very, very slow, but then you could just click a button and it would get you a nice high resolution capture of that video frame.
I have questions. Wait, so, okay, I have it going to my VCR. There's a thing going between that, I'm assuming using RCA cables or BNC.
Right, just an RCA cable.
Okay, and then that goes there and that's going into my computer. Okay, magic. Okay, there. That was the only thing that I was missing.
And then straight to Twitch, right?
And straight to a file on your hard drive for your personal viewing later, I guess. Or maybe if you're on CompuServe or something, or on BBS, you could share it with your buddies that way.
Annotate it.
I'll tell you what you were doing with it. You were posting it to Usenet. After you've chopped it up into 6 parts, so people could download it and then reassemble it, and then also posting it to your website that probably had like a rotating skull and some dripping blood lines on
and the rotating globe, don't forget that.
Yeah, I mean, yes, welcome to the World Wide Web.
And the autoplay MIDI canyon.mid in the background.
Ding, and blinking marquee text.
Lots of blink tags, yeah.
But for those for those who are listening, so anyone who can hear me right now, you do a lot of really great Twitter threads, and this is one of them where you kind of start your project and you walk through kind of as you're working on this project, you're kind of giving us a step-by-step, right?
Well, I wanted to know how it worked because I knew about the device at the time, but I could never afford it. And so I figured, well, I actually found one at the local junk store, and it was like $5. I'm like, sure, why not? So I just bought it, took it home, took it apart, and it's a circuit board with a bunch of chips on it. And I thought, well, why don't I just completely reverse engineer this thing? There's not too many parts on it. It shouldn't be that hard. So I pulled off all the chips and went through and digitized all the circuitry, turned it into a schematic, and figured out that there was a chip on there that had custom markings. So it was no standard off-the-shelf part. It was some custom chip, apparently, that the Snappy Video people had made. And then I was looking at it, I thought, well, wait a minute here. This is a pretty small company we're talking about. Would they really spring for a full custom chip? Or is it something else that's off the shelf that they've just remarked? And so I looked at the pinout and I tried to match it up with like different microcontrollers and stuff like that. And I couldn't really figure it out. So I posted it to Twitter and somebody almost instantly responded and said, oh yeah, that's a Xilinx FPGA. And I was like, what?
Jesus Christ. Wait, a Xilinx FPGA, like how would you be able to figure that out if a FPGA is configurable and you can turn it into anything? What am I missing?
You just look at the power and ground pins. So you look at the package. It was I think it was a PLCC part, but you look at which pins are power and ground, and that's kind of how you can tell. And the only thing that it matched up with was like one of like 2 or 3 different Xilinx FPGAs.
Okay. Thank you.
But your question's really good about the configuration, because the thing about an FPGA is that it uses SRAM cells to store the configuration, right? So that the SRAM cells give the FPGA fabric information about what gates are supposed to connect to what gates and that kind of thing. And so you need somewhere to get that information from when you first turn on the power. And usually that comes from a configuration memory, but this board didn't have that. So typically there's like a little 8-pin chip that's an EEPROM, like a serial EEPROM that contains the bit stream, but this board didn't have it. And I was staring at it and I realized what they were doing was bit banging it over the parallel port.
Yikes.
So when you plugged it in and you ran the Windows software, the first thing the Windows software did is it loaded the bit stream down into the FPGA.
That's interesting. Kind of like a Salier.
Yes, exactly like a Salier, except very different.
So I had one more question going. I didn't want to interrupt all the good stuff here. When you said you went to a junk shop, what does that mean? Is that just like a thrift store, or
there's a local electronics surplus store. I think it is the last remaining electronics surplus store in Silicon Valley.
No.
Weird Stuff closed their doors a few years ago,
like,
unfortunately.
Where? Like, that's what I wonder, is like all the ones I know are closed. So that's why I'm wondering.
Gotta drive south.
Yes. So this place is located in San Jose. It's called Excess Solutions.
Oh, it sounds like they had a lot of solutions to sell people.
They have a lot of solutions that they sell to people, including getting rid of their old junk and then setting it up so that somebody else can buy that junk for junk store prices.
Yes. Okay. Thank you for explaining what you meant by a junk store. Great. Okay.
So you can find all sorts of cool stuff.
Now back to the technical stuff.
Oh, I love that store so much. I go there all the time.
I've never even heard of it. Now I need to go.
You should go. Yeah,
I know.
It's great.
Maybe I should go today.
Support your local businesses, please.
Okay. Maybe not today.
Saturdays.
Yes, I will. Yes, I was going to say.
So if you can't make it there during the week, you can go there on a Saturday.
Yes, that's what I think. That's what I'm going to do tomorrow.
The only time I went, I ran into Eric.
Oh my God. Wait. You didn't even go like, hey, I'm going to go over to Excess Solutions. Like, you want to go with me? Sure, let's go. Okay, besties.
I was checking out, I think. And then I was like, oh. I know you.
Well, I honestly, if you went to Weird Stuff or Halted, like
I ran into past guests of the show at Weird Stuff.
Exactly.
Joe Grand once. Yeah.
Yeah, it used to be running into all kinds of people at those places. There was you do the triangle. So you go to Excess, Halted, and Weird Stuff.
Yep.
And then often you would see the same people. You're like, I think I saw that dude at Weird Stuff when you're at Halted.
Is there a secret fourth place, which is technically the
flea market?
Yes.
The electronics flea market. That is fantastic. And it's really too bad they have not been able to have any for quite some time because of the pandemic.
And now it's raining.
In the before times, you could go to this place, which was typically in a parking lot. They did it at De Anza College for a number of years. and then eventually at the Fry's parking lot in Sunnyvale until that closed.
Mm-hmm.
But you could go there and get all kinds of just strange stuff, typically electronics or ham radio related,
Mm-hmm.
that people would just dig out of their garages and get rid of.
Yeah.
So
I feel like I
really-
need to get my ham radio license. Damn it. Okay. Okay, so back to your so
Snappy
we know it's
Video.
a Xilinx FPGA. Because it could only match like these power in and outs. Okay, carry on.
I didn't get quite as far as the bit stream, but there are possibly people on the internet right now that are looking at that bit stream who also understand what each of the bits does
Mhm.
because they've reverse engineered that particular Xilinx FPGA. So again, this is the sort of the community effort coming into play. I reverse engineered the circuit board, and so the schematic for that is out there, and people that want to look into the bit stream can then sort of leverage that and figure out what the FPGA is actually doing.
Mhm.
I mean, we kind of know in concept how it works, but we don't know the exact details down to the gate level.
And a question, how the hell did you get the software to talk to this thing?
Yes, given that a modern computer, or did you also get Excess Solutions also had a junk computer for you to use?
Believe it or not, I used the computer that I used back in the day, and I didn't have to collect that one. I just kept it around because it runs Windows XP and has a parallel port.
Nice.
Did it also have an A
obviously-
drive, an A smaller 3?
No,
inch
unfortunately, no.
floopy.
It does have USB, which is also kind of nice because then I could transfer stuff over more modern
It's a
flash
technology
drive.
bridge.
Mhm.
Yeah, exactly. So it's an in-betweener. Some people call it a tweener computer because they can go from there back to some older
Oh,
technology computer.
so you used a USB thumb drive of some kind and not a zip drive. Is that
Right.
Okay.
Right. So I
Just
used the
wanted to check.
USB thumb drive to get
Mhm.
software onto the machine, which I found on the internet. Somebody has apparently got a page where they archive all of the software from this particular company.
Nice.
And so you can go and download that and try it out. And it's got an extremely 90s Windows interface,
looking at
which
it,
is quite
yeah.
a trip.
Are there are the graphics like totally weak sauce? Like they're
It's
just
not a
like-
square
yeah, they're-
window.
Is there a doctor listening to a disc at any point? Is there?
It is extremely curvy. Like
Yeah.
Yeah, it's got a theme for sure. It's a very 90s theme.
Mhm.
Yeah, in a sense, it reminds me of some of the more creative Winamp skins that you used to see back in the day.
yes.
Oh my god!
Winamp.
I don't know how Winamp was around for as long as it was.
It's back. open
People are
source
still
it.
using it.
Yeah, I know. I don't know what happens. At 20 years, retro things come back. I do like platform shoes; those are back. And so I have a ton of in style shoes
Now we're
now.
talking about shoes.
Look, I'm trying to pull the audience in so they can understand what we're talking about by like using other aspects that they may be familiar with.
So wait, are these what are these like the Linux platform shoes or are they Windows
Oh.
platform?
Sorry, I blew out. I feel like I could probably put like a Linux logo on a shoe for Halloween.
Must have been
That
done
would-
already, but
That would be acceptable. Probably, but look, the people I work with are so
Fit right
young they
in.
wouldn't know.
You could probably order Linux branded shoes from China.
Probably.
They might have reused the Ubuntu
Tux.
logo or something, but I bet you they're out
Probably.
there.
With just a little change.
I was in, I think it was Shenzhen one time, and I saw a shoe store, and at first I thought it was the Apple store because it had the Apple logo, but the scale wasn't quite right. Like the Apple was a slightly different shape, but it was still white, and it had like the backlit thing that they have going on. And I looked through the windows, and I didn't see any phones. It was all shoes.
Yes. It's like that time when I saw what appeared to be a Burberry store, but it was like blueberry, but it was like in the style of Burberry. Yeah.
non-rectangular windows.
Trust but verify. It's been a lot of time on the verification. That's my
Yeah.
advice whenever you go to Shenzhen. Verify a lot. Spend a lot of
you
time.
otherwise you don't really know what you're getting. You know, it's interesting that I bought a bunch of 6502 processors from China,
Mhm.
but because of that verification suite that I wrote, I could literally plug the chip into a socket and then run the test and then figure out what it actually was.
Nice.
Surprisingly enough, most of them passed the test.
Yeah, that's what I was going to ask before. For some of these, chips you have to put on your device for testing them, do you just put them on the device, see if it works, or do you ever make little kind of testers for them?
Oh, I have a fixture, at
Yeah.
least for the 6502, which is the complicated one.
I guess here's my follow-on question for that fixture. And, obviously we've already talked about how this was already open source software, and presumably you've helped improve that over time. The question I have is, like, have you considered, like, on a Tindy store or whatever, to go, here's a fixture if you need to verify your 6502s? Or you just put out your shingle and you're like, I'm a 6502 verifier. Pay me to verify your sources.
I have considered doing the Tindy thing before. Typically what I'll do is I'll release something as an open source project, and I won't sell it because that is a lot of work. So
but someone
taking
else
care
does,
of a
right?
store and shipping stuff out and just worrying about stuff going in and out of stock. I mean, it's certainly something I could do. It's just not something I'm really interested in doing. So, like, you look at the sound card clones and stuff that I've designed, and I don't sell them. I just release designs so that other people can sell them.
Yeah. I totally get that.
And they do, right?
Oh yeah, definitely. So it's kind of funny, actually. If I go on eBay and I browse through vintage computers, I will often see Sound Blaster cards that are sold as reproductions that are my design. It's just somebody in another part of the world has gotten some boards fabricated, and they've stuffed all the parts and soldered them in place, and now they're selling this thing on eBay. And
how do you feel about that? Yeah, I mean,
drives the price of the originals down, right?
Hopefully. Exactly. Yeah, those cards are a lot cheaper now.
And that was the goal.
That was the goal. I want people to be able to enjoy that old tech without having to be worth a lot of money.
Speaking of old tech, you also have created some 555 timer and 741 op amp, right? Disassembled kits. Like, we talked about the Monster 6502, the individual components, but for the mere mortals among us, there's a level 1 version of those.
Well, that's where it started. And this was a seed that kind of got planted in my head when I was pretty young in the 90s, because I had these Radio Shack data books, which would show you all these different chips that Radio Shack sold with a little bit of information about it. And, of course, now I find out it's all copied out of the original data sheets. It's just Radio Shack wanted to get you into their store. And so, of course, it was all branded as Radio Shack. But each one of those data sheets, many of them, not all of them, had a schematic at the end. And I remember looking at that when I was younger and thinking, man, this means that if I just had some transistors, I could probably wire them up and turn them into the chip. But then I saw these weird looking things on there, like transistors that had 2 emitters and stuff like that. And I kind of got discouraged because I don't know where you could buy a transistor that's got 2 emitters. It wasn't until much, much later that I found out that's just 2 transistors connected in parallel, with the base connected in parallel, the collector connected in parallel, and then the emitter is just left as separate emitters. And it's used as part of a current mirror structure. But I didn't know that because I didn't really know anything about how chips are designed. And so it wasn't until later on, after college, after I'd learned all this stuff and worked in the industry, that I realized that chip designers, as a matter of fact, did prototype their analog chips with physical discrete transistors. And often they did it using something called a kit part, which were actual process transistors from the IC process that they were targeting, built out in a little metal can. And you could plug that into a breadboard and build up a circuit and essentially run an emulation of what that chip would be like on that process. And in the days before computer simulation, or before cheap computer simulation, that's how every designer did it. In fact, many designers continued to do that years after spy simulations got to be more popular, simply because the real thing is always going to be more accurate than the simulation.
Yeah.
And so that's kind of where that started. And then at some point I thought, well, I should try actually building one. And so I did it with a 555 timer on a piece of wood. And so I had little transistors and resistors and stuff like that all soldered together. And I tried it out and it worked great. In fact, if you want to see it, it's at the Evil Mad Scientist shop. So they have that set up kind of on display. And that was sort of the initial prototype. Alvaro, I think you've seen it before.
Oh yeah, I've seen all these. Yeah,
there's probably pictures of it around. I think I've put it on Twitter before as well. But that was kind of the initial prototype. And it was at a Bring a Hack. I'm pretty sure it was at a Bring a Hack dinner that I was talking with Lenore about it, possibly Wendell, but definitely Lenore. And I thought, well, what if we just turn this into a kit? And Lenore's like, well, we do kits all the time. Yeah, we could definitely do that with you. And so that's kind of where we started that whole thing. And so that was very much a collaboration because I already had the schematic, right? Because it's in the data sheet, right? We had transistors and all that picked out. And I had a little board layout that I put together. And I went back and forth with Wendell like 100 times, dialing in every single little silk screen placement and every single little trace, getting everything just perfect. Because that's one thing that they're really good at, is that sort of attention to detail, right? So you look at any of their products and every single one of them has just this extreme attention to detail, which is one of the reasons why they're just so well done. And so it was tough. Let me tell you, it was tedious going through all of that process. But when you're done, you've got something that's really polished and makes a really great soldering kit. Yeah, no,
I've seen them at the shop, but I also see so many people posting pictures of them because it's just and you can use them, right? It has this very large, like obscenely large IC legs, I guess, or you can get them and you can actually connect to it and still use it as a 555 timer.
Yeah, in fact, the manual for it, which you can download, you don't have to buy the product to get the manual. It has a bunch of ideas for things to do with it. So obviously you can build circuits around it. So you could build your little blinky lights or your tone generators and stuff like that. But in the user's manual, there are experiments that you can do with the internal guts of the chip, right? Normally a chip is just this really tiny thing and you can't get in there unless you have a FIB, focused ion beam machine, or a laser probe station, which, you know, some people in the reverse engineering community have access to tools like that. Most people don't. So for editing a chip, it's not easy to do, but with a kit like this, you can edit it, right? It's all human scale. You can get in there with an oscilloscope and probe internal nodes. You could remove transistors or replace them with other components. You could change resistor values. You can kind of do whatever you want. And so we have a couple of, I guess, sort of question and answer type of things just to give you ideas about things that you could try. Like, what happens if you remove this transistor? How does the chip behave? And so there's a little bit of an educational aspect to it as well.
Yeah, I think for those people who are really curious about how it really works, the ability, as you said, to get down, to have it at a human scale where you could probe at every node on the net list to understand what will impact it and what the outcome will be, I think is very valuable, particularly for electrical engineers or budding electrical engineers.
I would also recommend it for people who want to get into chip reverse engineering as well, because honestly, if you've got a chip and a probe station, the hardest part is, I mean, there's the physical aspect of things where you've got this really tiny tungsten needle that you're trying to drop onto the surface of the chip. But first you have to blow through the passivation layer. It takes hours and hours of work to get everything prepared and ready to be able to probe a single node. And it's not anything that's particularly challenging intellectually. It's just a physical dexterity challenge and an equipment challenge. But once you get through that, at that point, it turns into a logical challenge. Like, what am I trying to measure? What am I trying to look for? And that's all stuff that you can do with a kit like this.
Yeah. This, like the more practical, like actual hands-on stuff, right? And for looking at pictures, always point people to Ken Sheriff's stuff. Like if you want to reverse an IC from pictures, that's a whole other monster.
Yeah, his stuff is very good.
Yeah, so actually I would say that in many ways what you've put, you know, this particular project is very interesting because this is typically what you would have somebody at an undergrad electronics lab do as a project. Something along those lines.
Yeah, when I was going to school, I lucked out. And so I went to Cal Poly in San Luis Obispo, and they are very focused on an approach which is essentially learn by doing. It's actually the school's motto.
Yeah.
The way they implement that practically is that their electrical engineering classes will typically pair up with a lab class.
Yep.
And so you have to get in there and get a proto board and put transistors into it or put op-amp chips into it and build all these practical circuits. One of the labs that they have, you get to build an op amp out of discrete transistors.
Mm-hmm.
And so that was kind of one of the inspirations for this, because then I realized that, well, hey, wait a minute, you can actually build circuits like current mirrors and differential amplifiers out of discrete transistors, and it works perfectly. And for some reason before that, I hadn't really thought that was possible. But once I went through that class, I realized, well, you can do it.
Yeah, I feel like that those are the things like I regret not absorbing more heavily yeah.
Well, and it's hard to absorb without
we built all those things, but what I like about it is like, okay, so let's say you, for example, like for me, like because I basically ended up just doing software, you forget all this stuff. So it's nice that I can go back and kind of remember, oh yeah, this is what's supposed to happen at this node, this is what happens at this node. It's a nice refresh. It's also really good for even high school students or younger who are just trying to figure out, like, do I even want to do a degree in this?
Right, exactly. Like it's something that you can just sort of play with and get your hands dirty, and it'll pretty quickly become apparent if this is something that you're interested in or not.
Yeah.
Yeah. It's a good filter.
Yeah, exactly.
And I don't think we covered this, but why tube time? What's up with that?
Yeah, what's up with that?
We're calling you tube time. Why?
Tube time. Why tube time? Tube time.
Tube time. So that has an interesting story behind it too. And the name itself dates back to Maker Faire, to the second. No, it was the third
early.
Maker Faire, which was the second Maker Faire that I went to. And the projects that I brought were all Nixie tube clocks or CRT, cathode ray tube clocks. And so the first year that I went, which I think was 2007, I called the exhibit Anachronistic Clocks, which was kind of cool because they're anachronisms, right? Because they're clocks, but they're made out of old parts. But it was also a pun because I thought, well, anachronistic, but it's the clocks that tells the time.
Yeah.
Anyway, it was not a great name.
By the way.
Yeah, it wasn't great. So, you're counting.
Yeah, I was with the first one, so you're at 2.
Some may say timing. Anyway, no. So the second year, I decided to go for a shorter, snappier name, and that's kind of where I came up with Tube Time. So it's time for tubes to tell the time, kind of a thing.
Oh.
And so I started a Twitter account to try and drive traffic to my blog, which I didn't really understand how social media worked at the time, because if you have like
Nobody
0
did.
followers, you could tweet all day long and no one's ever going to see it.
Well, it's
That's
worked out so far.
Yeah. So what happened is that I don't know, I kind of let the Twitter account be fallow for a number of years. And eventually I started posting a few more pictures of some projects and stuff. But what really got it off the ground was the Monster 6502, because I posted about that. And then I had friends and coworkers and stuff like that who were interested. And I sent them the link and they saw it, and they had Twitter accounts and they retweeted it. And they were connected to other people in Silicon Valley. And then pretty soon, a bunch of other people saw it. And then I started to get more followers. And it sort of snowballed from there.
Okay, so your coworkers had friends, and that's what helped. But okay, just
I mean, I have friends too, but I have a lot of non-technical friends, and they're not on Twitter. Yeah, or they're on Twitter, but they use it for what everyone else uses Twitter for,
as a newsreader.
Yeah.
I'm gonna repeat it again. Like I'm sure most people already follow you, but if not, you have some pretty awesome threads and all sorts of, like, a lot of reverse engineering projects, but also anything, I guess, things you find interesting. I assume is the criteria for putting stuff on there. But they're
things I find interesting is a good way to put it. Yeah, so it's anything that kind of strikes my fancy. I mean, I sort of use it as like my online lab notebook. So if I'm working on a project, it's like really low friction for me to like snap a picture with my phone and then maybe type in a little bit of snark and then send it out and then other people can see it. And then later on, if I need to refer back, like, how did I connect those wires? Then I could just look at the picture, look at the tweet, and okay, that's.
It's a little crowdsourcey, though. It's a crowdsourcey.
Well, you can also ask questions. Yeah, it's a lab notebook with public comments.
Yeah, dear Twitter.
No, I like how you put it, a lab notebook kind of thing. Yeah.
So one of the projects or Twitter threads that I remember was you looking through kind of how ancient some of our electrical grid is, particularly in Butte County, that
How
is infamous.
flammable it can get.
Yeah. So that was for people that aren't or are not living in California. We have been having a lot of problems with wildfires in the past couple of
What?
years, and I mean the cause is complicated, right? There's a whole bunch of factors that come into play. One of them is that California is in general a very dry state, but there are places where it's wet. For the past probably 100 years or so, things have been unusually wet, but they're starting to dry out again. We also have a lot of agriculture, and agricultural type grow operations, they use a lot of water. So a lot of the water in California goes to growing almonds and other crops that get sent all over the world.
Mostly almonds, though.
They
almonds, require a lot of water.
They take a lot of water. And so there's this sort of ongoing battle between the cities and the agricultural enterprises on who gets the water. And it's tough. It's very difficult, especially with climate change and all of that, increasing temperatures and all of that, and manipulating weather patterns in ways that aren't always predictable. So that's part of the challenge. The other part of the challenge is that we have, at least here in Northern California, an electrical utility, PG&E, who is, they're not a well-run company. And in fact, they have wound up in a lot of trouble before. They, as a company, have been convicted of a felony multiple times. And so they had a gas explosion in San Bruno, which is south of San Francisco, that blew up an entire neighborhood. Yep. And that's because they had a unmaintained gas pipeline, high pressure pipeline. This is one of these distribution lines. It's not going out to customers. It's going out between multiple distribution points. And so they're running it at a very high pressure. And it was undocumented. So they had no drawings from back when it was built. It wasn't built correctly originally, and they weren't doing correct maintenance procedures on it, and it exploded. It was not a good time. So they got convicted of a felony there. What happened also was they also have a whole bunch of electrical transmission lines, which are similarly poorly maintained and poorly documented. There's a particular set of lines which is up in Butte County, and this is a county that's in the foothills of the Sierra Nevada mountains, kind of on the eastern side of California. And in the 1920s, PG&E had acquired a set of distribution lines that were built by a different power company to bring power from a hydroelectric dam down into the Bay Area. I think it was Fremont where they were first providing power. So they bought the lines and just used them, and apparently never bothered to maintain them. So these lines were 100 years old, and we had a spot of really bad weather. So one year we had really high winds. Things were very, very dry. The fire risk was really, really high. And one of these lines failed. So there's a particular insulator that suspends the wire, and the insulator hangs using a hook on essentially a hole that's drilled in a piece of steel. That's the crossbar. So this is on a power pylon that looks like one of those sort of giant metal structures that goes across the countryside. So this insulator breaks off because the hook wears through 100 years of wear and tear of the wind pushing it back and forth. It wears through, it snaps, the wire comes down, it bounces off the side of the tower, which causes a shower of sparks. Those hit the ground, and it started one of the largest wildfires in California's history. And this was the Camp Fire that swept through essentially uncontrolled and burned down the entire town of Paradise.
Very quickly. Shockingly
very, very
quickly.
Well, the high winds help with that.
Yeah, the high winds continue to drive it. The fire departments in the area were just completely overwhelmed. There was essentially nothing they could do. It was a tough time, and it was tough for me and my relatives too, because I had grandparents that lived there. Thankfully, they had moved out of Paradise months before the fire hit, so it was a very close call. But I have an aunt and uncle that spent months up there, like renovating their old house and fixing it up and selling it. But I think it was only a few weeks after it sold and someone bought it that it burned down.
Yikes.
Jesus Christ. Jeez.
Yeah, so it was really, really difficult for everybody involved. And the worst part is, so the Butte County DA did a whole investigation on it, and you can read the report. It's got great pictures and all of that. Most of what I did in that Twitter post was essentially repost those pictures along with sort of an abbreviated version
with
of the
human
investigation that
understandable.
they went through. Yeah, trying to make it a little more understandable, because I mean the thing is, it goes on page after page after page with
Yeah.
lots of technical detail and
Yeah.
timelines and stuff like that. If you're into that thing, it's very interesting. But what so they ran into a number of problems. One is that PG&E apparently doesn't keep records, which incidentally happens to be illegal, but they've been doing this for a really long time,
But also convenient.
and nothing really bad happens to them for doing it that way. And so they just keep doing it. So they don't have any records from before the year 2000. And the best that the investigators could do was find a paper from a really old electrician's magazine that came out in like the early 1920s by the original company that built the power lines, describing some of the innovations that went into it.
Wow.
That was literally the only documentation they
Jesus.
had. Yeah, it was not good. And so this whole thing just sort of plays out, and PG&E got fined something like $2 billion for doing this,
Yep.
which, I mean, it's great. I'm glad they got fined. The problem is that for various legal reasons, they were able to take the amount of money for that fine out of a state fund that was set aside for victims of the accident of the fire.
Jeez.
Wow.
So in reality, PG&E didn't pay for any of it, because they figured out a way, their lawyers figured out a way around it. So the worst that the judge could do in that particular case was require all the executives of PG&E to get on a bus and take a tour through the burnt streets of the city of Paradise.
Jeez.
You got off easy, yeah.
Yeah, so I don't know if any of it sunk in, but so one of the conclusions that I came to was that the reason that PG&E has been able to do this and not have individuals within the company who are liable is that they have a system set up to diffuse responsibility. So in other words, every decision is a group decision. So there are lots and lots of people involved with each of those decisions. And the purpose isn't to make better decisions. The purpose is to make sure that no one person is entirely at fault should something bad happen. Right? Because legally, you're not going to go and try and put 100 people in jail for something like this. I mean, you can't do it.
It was a group decision, guys.
Exactly. And so that's what they do. And so they have this organization set up in a particular way that no one person is responsible for that decision, because otherwise there definitely would have been fines individually and probably also jail time as well.
Yeah.
But they've figured out a way around it, which it's really unfortunate. It's really, really unfortunate.
I was just thinking back to the diesel issue
Volkswagen?
with
Dieselgate,
because I think some engineers, somebody
got scapegoated.
I think there were a couple of people that got scapegoated, but I thought there was somebody that was explicitly held liable there. I could have swore.
Yeah, but that's rare.
It is exceedingly rare. But for this, the one thing that stood out to me, and I don't think it's a surprise, that maybe you can elaborate this more, at least from my understanding, is a lot of our electrical grid across the United States, Texas would probably be another example of this, is very antiquated and has not been updated. And
it's expensive.
It's expensive.
Nobody wants to pay for it, yeah.
Yeah, that's very American of us to not want to pay for normal updates and just kick it down the road. But I'm not here to...
you should talk to my friend about dams, because...
no.
If you think power lines are bad...
I've heard some of the stories.
Oh, yeah.
It's a real problem here. And I think what happens is there's this sort of sense where there's some brand new thing that comes along and everyone's super excited about it, right? It's this new thing. It's like really sexy. Everyone wants to get in on it. And everyone does get in on it. And there's a whole bunch of companies that start, and there's a whole bunch of companies that collapse, and there's tremendous amounts of activity and startups and this and that and the other. And people build all these different variations of a thing. And then it sort of settles into, well, this is kind of the right way to build this thing. and then it starts to kind of get tidied up. Maybe there's like 20 companies that are doing this, and they're buying each other and merging, and then they start streamlining and starting to squeeze more and more money out of it. And then it's not really the new thing anymore. It's just kind of the thing that is. And then it's boring. And then nobody wants to have anything to do with it because it's not a growth industry anymore. And then people start not paying attention to it at all. And then they start skipping out on the maintenance costs.
Yeah, even though we all need it.
So you just described the technology adoption curve there.
Exactly. It's the technology adoption curve. And it's not just electricity, because electricity is a fairly new thing, right? I mean, electrical distribution as we know it is maybe 120, 130 years old. I mean, 1880s and 1890s was when it was sort of first made a practical thing.
I don't think many houses even had electricity in the 40s and 50s, depending on where you lived.
Yeah, it took a long time to get electrification out to particularly rural areas.
Yeah. We're still working on internet for some areas too.
Yeah.
So I think that shouldn't be a surprise.
Yeah, the internet is kind of the sort of analogous to that as well. Yeah, I think we're going through the same curve there as well.
Mm-hmm. But the one thing that you, in your explanation of the technology adoption curve, that also seems applicable here, that people don't want to do the maintenance per se, is also that, usually what also lags is the regulation, the government regulation of it, as it, when it's new, the government doesn't know what to do about it. So it takes a long time for them to figure out if they're going to regulate it, how they're going to regulate it. But in this, it seems like we never quite got to regulation, or we've deregulated it, I think is probably what's most likely happening.
Not enforced.
Yes.
Yeah, I actually talk about this in the Twitter post a little bit, and I think it's really easy to fall into I don't know what you call it. It's sort of an ideological trap where you say, oh, the problem is that PG&E is not regulated enough, right? But other people of a different political ideology would say, well, PG&E is regulated too much. We need to deregulate them more. And I think that the real answer is complicated. It's not any one thing or the other, but what it is that you have a dysfunctional organization, which is PG&E, being regulated by a dysfunctional regulator, and that's the California Public Utilities Commission. And if they were organized better, and if they did a better job at what they're supposed to do, then we wouldn't be in this problem, right? We wouldn't be in this situation.
Is this
so
based
the
on
regulator
your
that's supposed to? It's
so
not based on my reverse engineering. There's been some really good reporting that's been done. Unfortunately, I forget the name of the paper, but again, this is all on the thread.
Well, I'm positing as reverse engineering the organization, reverse engineering the process of how we landed here, not necessarily the electronics.
You could, yeah, and reverse engineering the organization. That's more something that maybe a reporter or somebody would do.
Yeah,
but it is definitely a form of reverse engineering because you're trying to figure out how this particular situation happened. So there's been some very good reporting done on the California Public Utilities Commission, and let's just say that they're having some extreme difficulties. They're not doing a good job regulating the utilities in California. For example, there's things like they don't have a master list of all the utilities that are under their purview. In other words, a list with contact information.
Yeah, how do you regulate
like
if you can't talk to them?
It turns out there was a municipal gas supplier that they were supposed to be regulating and collecting fees from, and they never bothered to collect the fees from them for 20 years. So the utility was collecting a 2-cent surcharge or whatever it is. I forget the exact details, but they had never bothered to remit it to the state of California, and CPUC never bothered to follow up with them about it for 20 years.
Jeez.
And that's just one example. There's numerous examples, and it's not like they're understaffed. They have 2,000 people working for the organization at their offices in San Francisco. So what we have is a dysfunctional organization that's not doing a proper job regulating a dysfunctional company that's not doing a proper job providing safe electricity to Californians.
But isn't it possible that the reason why the Utilities Commission is dysfunctional is because, and I don't know this for sure, I'm just positing that maybe this is what's happening because I've seen it in other areas of government where the companies who are the ones that are supposed to be regulated by the commission end up leaving private to go into public service, and they end up taking in those jobs and roles, and they just are very lenient because they know they know their former company and those guys that are working there, and they're just like, don't worry, we'll just worry about it later. Is it possible that may be happening?
That's a situation. That's a situation called regulatory capture. I don't know if it's happened in this case.
Yeah.
It's certainly possible. I know it's happened in other cases.
Yeah.
It's definitely a thing. And I think part of the difficulty is that in order to regulate an industry, you need people to run the regulator who understand that industry. And a convenient way to get people that understand the industry is to get people that have spent time in that industry. And then what you're counting on is the fact that they're going to be honest and ethical about the way that they then deal with the companies that they either competed against or worked for. And
that's true.
Obviously, that is lacking in some cases. Not all cases. There are good people out there who are doing a good ethical job. And of course, we never hear about those people because whatever they're regulating, just everything's going fine. It's right. It's the negative cases. It's the bad situations that we hear about.
Well, I'm sure somebody would probably say nobody ever got rich by doing the right thing.
Yeah, that's a tough one though. I think it is possible to get rich doing the right thing, but we always hear so many examples of people who get rich by doing the wrong thing that we kind of give up hope.
Yeah.
Yeah, that's tough. So, going back to reverse engineering, do you feel that reverse engineering in many cases can be ethical because of, because it's trying to understand, or do you think that it's often being used to do the wrong thing?
Ethics in engineering.
And I'm really sorry for putting you on the spot here.
No, this is a really good question. And I think it's particularly important for people who are into reverse engineering to think about. But it's also important for people who are into engineering in general to think about. It's not just reverse engineering.
Yeah.
The most obvious example that people like to use are civil engineers. A civil engineer who is a licensed professional engineer is responsible for the safety of all the structures they ever designed, right? If they put their seal on a drawing, they are personally responsible for it. So if I'm not a civil engineer, I'm also not a licensed professional engineer. But if I were, and I had that seal and I put it on a drawing, and 30 years later, that building or that bridge came down, I would be personally responsible for it.
Yeah.
In court.
Yes.
Like there would be official proceedings going against me. In a lot of the other fields of engineering that don't necessarily require that kind of a official seal, they don't require you to be professionally licensed, I still think there is some amount of responsibility for that design. So for example, if I'm working for an Amazon and I'm designing a hardware product that's got a microphone in it, I'm going to be very interested to understand how this is going to be used and how it affects the privacy of the people that are using it. And so if I'm involved in any meetings or decision making, this is something that I'm going to bring up. And if it's something that I feel is unethical, then I'm not going to work on it. But again, that's a decision that an individual is going to have to make.
Yeah. Oh man, so many things. So I think both of you did like a double E or a CompE or something like that, right? Because I know. So, yeah. So
electrical engineering.
Yeah, exactly. Yeah. I know so I did CompE, which is related, but I know a lot of the double E's were going through and trying to make the decision for themselves whether they would bother with getting a PE, getting, their professional engineering certification. And I don't think many did, because I think it very much depended on what you were planning on doing.
Your industry.
Yeah. Yeah. And I think
I don't know many double E's with a P.
Yeah. So there's that.
I know a few. I mean, it really depends on the track that you take. Mostly power,
Yeah, the utilities and public infrastructure, right?
Yeah. The other thing was that during your time, do you guys remember there being much discussion around ethics in your coursework?
Not a ton. I mean, like it might have been like a 1-credit class at some point.
But was it required?
Probably. But I don't remember.
That's fair.
When I went to school, which was, well, I won't say, but when I went to school.
I think I'm still older than you, so don't worry about it.
Okay. So when I was going to college, we had no requirement for any kind of an engineering ethics class.
Mm-hmm.
The closest that I got to it, I think, was probably a general ed class I took on philosophy.
Mm-hmm.
And we had actually a decent discussion about ethics, not necessarily in engineering, but ethics in general.
Yeah.
I would say that's the closest we got. In fact, that's one of the reasons why I think it's important for engineers to get a breadth of study and not just to go to like a technical college and just study this one thing. It's really important to take classes in philosophy or literature or writing or whatever the case may be. There's just so much else out there besides engineering. And even if it's something that you're not interested in, there are still things that you can gain from that. Like if you take a biology class and you learn about how, the Krebs cycle work, how do cells generate energy or whatever it is, maybe that'll seed some ideas for a project that you actually do find interesting. Like there's some cross-pollination there as well. But I think just to make yourself a well-rounded person, it's important to understand and to study lots of different fields.
Sure.
I mean, if anything, you'll get an appreciation for the work that other people do.
Yeah.
That is a very Bob Moog style of engineering, which is, just look at where the influences come from. But I will say that, I took my intro to ethics class. You talk about Hiroshima, a couple of things. But there was literally one class session when I was taking assembly or, programming. I don't remember what it was like. It was like part 2 of digital lab or something like that, which was just basically, assembly programming. And we talked about hacking and whether it was ethical or not. And that was about it.
It's all about what you do with the information you learn, right? With reversing.
Right.
Like, I personally feel nothing's wrong with taking something apart and learning about it. What you do with that information, that's where it starts to get more interesting. Ethically, I think.
Yeah, definitely.
Like if it's just for your own learning, then do whatever you want.
Yeah, but we're definitely at this point, and I know Alvaro has read this book, as have I now. How the world ends, like it is. We're definitely at a point in history where we're seeing how money is playing more of a factor.
Yeah, the book is called "This Is How They Tell Me the World Will End or Ends." Yeah, and it's
I'll
about
have to look that up. I haven't read that yet.
It's pretty good. It's about the marketplace for exploits and how much money there is in finding vulnerabilities and selling them. Not to the companies.
and maybe you're in the government, but you end up like selling them on the side.
Yeah. It talks a lot about, it's interviewing people, but about, the ethics of selling exploits.
So for people who are independent contractors, shall we say, people that are reverse engineering just for their own education, or maybe they're doing it and just as kind of as a hobby, there is the concept of responsible disclosure, right? So if you find something that's usable as an exploit, there's a whole system for letting these companies know, and a whole procedure that, the idea is that you follow this procedure. This is the ethical way to do the right thing, right? To let the company know that they have to fix this problem. Now, I think what's also interesting is the situation that comes up when you're a reverse engineer or hacker who's working for government. Right. So say that you're an engineer, you work for the NSA, and you're not disclosing these vulnerabilities to those companies.
Yeah. Yeah. That gets
right. Or maybe you're
tricky.
even creating vulnerabilities. What do you do? And I think we can kind of find an analogy if we look at this is going to sound really random, but think of the detonators that were used for thermonuclear weapons. That was designed by an engineer. There was an engineer out there who I think he worked for Los Alamos, and he designed the something called the X unit, which set off the explosive charges inside the thermonuclear weapon that would make it go off and make a gigantic explosion and potentially kill a lot of people. And there's a really interesting book to read about it. It's called Command and Control by Eric Schlosser, and he goes into a lot of the details about the design of some of the weapons and the X unit. And it's basically like a camera flash unit. It's got a high voltage generator and a capacitor, and then it discharges. I mean, it's an engineering problem, right? You look at it, oh, okay, this is an interesting engineering challenge to design. But the guy who designed it was disappointed with the way that Strategic Air Command was using his device. And the book goes into all the details, but there's this tension between the generals who are running Strategic Air Command and the engineers and scientists who are designing the weapons, because those people didn't want these weapons to be used irresponsibly.
Mm-hmm.
They were dead set on that. But the philosophy of the generals was very different. They said, well, we want a weapon that can't be easily disabled, right? So the engineers wanted to put a lock on the detonator. They wanted to say, you have to enter a code before this thing will even arm itself. And we've got to have multiple ways of disarming it, and it's got to be really, really safe. So number one, it can't accidentally go off. And number two, it can't go off if someone who's unauthorized gains access to it.
Yep.
And Strategic Air Command said, no, we just want a big red button.
Because they're not thinking about, what if someone's like the football is usually what we refer to. Someone trips and like a button actually gets jiggled and smashed. What if someone just makes like an end zone run to go smash that button?
Or a disgruntled employee. It's like, you know what?
Yeah, exactly.
I quit.
You just don't know. And so the engineer who designed the X unit, he managed, he pushed really hard for it, but he got his combination lock on it.
Yeah.
And it wasn't until many years later that he found out that the installations that used it, Strategic Air Command and all of that, they had a combination on it, and it was all zeros.
Jeez.
Whoops. Yeah. No, it's a hard question, right? And you said they would be used responsibly, but that's such a like individual, like a perspective thing, right? Like the general might be like, oh, it's responsible to use it, and then just like end earlier, like end the war earlier, kind of thing, right? I was like, oh, but you just killed 1 million people. Like it's really freaking tricky.
This
is where that ethics class comes in. Like
this is where the ethics class
and philosophy
comes in for sure. And philosophy.
Let me put it this way: doing a MBA, I got more ethics training than I did in my undergrad. For obvious reasons, because it was post Enron. It's like that had just happened.
Whoops.
But at least let me put it this way: like probably the key question to ask, like that I use to this day, is like, would people choose differently if you told them the truth?
And the answer is yes. Then
you have an ethical conflict that you have to resolve, which is why like I feel so strongly that you still want to make money. Tell people, hey, this is, like have the ads free version. Have that, like if you're using our data to do stuff, give us the offline version. Let people buy the offline version of the software and the algorithm. We can, people want to do the extra work, let them do the extra work to like quantify it, to have all the data on themselves and munge it.
It brings us back into engineering ethics again, because we've all been on the internet for a long time, and we see all these dark patterns too. Like you go to a website, and particularly when they're doing the GDPR stuff, where they have a dialogue that pops up, it won't let you browse the site easily, and it says, "Do you accept these cookies?" And they have the giant green button that says, "Click me, yes." And then you have to click through like 8 pages of stuff to get to the really tiny text that says, "No, thank you."
Yeah.
Or I just need to accept the bare minimum.
No, and
ones
it's somebody's job to make a UI that will trick you into clicking yes, right? It's
So as an engineer, would you design a page like that? I know in my case, I wouldn't.
A UX design, but the thing is, like, is how much of this is product management versus you?
Well, somebody's making that decision
UX?
and somebody's implementing it, right?
Yep. Honestly, I think people are so depending on what type of company you work in, people are so fragmented that they don't have time to put all the pieces together to realize.
Some people just don't care. Like it's like, oh, this is harmless, right? Like it's just a cookie, whatever. But you could make that different levels.
So I guess I know that we've been talking for a while, but I guess the question I have is like, okay, so we remember Google Glass, we remember Snapchat glasses, and now there's the new Ray-Ban. Is that Facebook's glasses?
Facebook, I think, yeah.
Yeah. How many times are we going to do this?
As long as people keep
Like, seriously.
buying them.
Like, I don't have a way, now I could, like, at least with Google Glass, I could say, oh, there's a glass hole. I may know them and I may like them, and I could at least give them a cover for it to say, hey, can you just not like flip it up or
I
something like
remember
that?
those covers.
But now, like those Ray-Bans, I can't even tell if it's one of those or not. Also, as Amazon also has a set of glasses too, or maybe it's more like headphones, really. But the point,
I
is,
think it was like something that may have been more popular. I want to say like 2012, right? You saw in Silicon Valley. I mean, it's a bubble. You go outside of Silicon Valley and things are a little different.
They don't know anything.
Honestly, I haven't seen one in person in such a long time. And I'm hoping that it was just a fad that didn't last and that people just aren't interested in that kind of a thing. But I may be wrong.
The Google Glass in particular?
Well, any of those cameras that you wear on your face.
Well, the Facebook one just came out a couple months ago, so yeah,
it's not
and
like
you can go buy them in the store.
Days.
Yeah,
we would need to interact with strangers.
Yeah, I think that's a separate issue. Like I know there's a pandemic, and this is totally dating this this episode when aliens find it in the future.
Oh,
but
hello, I come in peace.
I don't know.
Also, any aliens listening, I wasn't there. That definitely was not me. Please do not confuse me for the other one.
Yeah.
The other tube time. Seriously, every time I think of tube time, I just think of like there's somebody in a subway car going, what time is it? It's tube time. It's tube time. And they're going to dance.
With a Z.
There's definitely a music video for that.
Tube times.
It may only be in my head, but
for now, you can use your Snappy Video Snapshot to do a slow motion version of your music video capture.
I could, but I would need to hire some dancers. So maybe
shit.
one of you can help me with that.
I know someone who does choreography.
Alvaro, I know that you are well skilled in dance.
If you mean I had to have hip surgery because of dancing,
and I'm gonna have hip surgery. In the
insurance
future.
won't cover it, unfortunately. So
hang on, I got to write this down. Do not get into dancing, otherwise you will need new hips.
Those hips don't lie, but they also break down.
Yeah. Oh, they don't lie. It's like pain.
Yeah, honestly, if there's anything I could tell to engineers, really use a good chair. If your butt is hurting or whatever, really work on your posture. Because let me tell you, when your hip goes, you can't not be on your hip. Doesn't matter.
We're going to go into infomercial. If your butt is hurting, you should get.
If you experience butt hurts, do not use Happy Fun Ball.
I will say that particularly people that are into engineering or technology or reverse engineering or that kind of thing, don't forget about your own body, because you have it for a limited time, and if you don't take care of it, it's not going to do well. So get plenty of exercise and eat right.
I can confirm. I can confirm this.
And it doesn't take much. Like if you go for a walk every day, it's going to do you a lot of good. So I use one of those little apps that you put on the phone that basically just tracks your steps.
Wow, we've really covered all the topics here.
I need to reverse engineer that app to see what day. Anyway.
Well, that was the last episode. You should have listened.
I think it's pretty clear we're going to need more episodes to cover, because we covered like a 10th of the projects we worked on, I think, like the reverse engineering projects. Before you go, though, we have to ask the question we ask everyone, which is what are some of your favorite tools that maybe people haven't heard of or just you think are great?
Yeah, that's a good question.
What's a tool that you could not live without?
A tool that I can't live without. Well, I'll tell you a tool that I use a lot, which is the Salier logic analyzer. So I know everybody uses that too, but I use it. I have a little bit of a love-hate relationship with it. And it's one of those things, and I think it's probably not so much a Salier problem as it is a Windows or a Linux problem. But Salier will push your USB stack to its limit. Yeah. And if you're running a computer or an operating system that can't quite handle it,
you got to turn down.
You're going to have a bad time.
Are you using it on your Windows XP with the parallel port?
It was really hard to find, but I managed to find that super early parallel port Salier. It was something that was designed. I mean, it was very obscure. No, I'm kidding.
No, I was gonna say I have all of
Like,
them. And
The salient folks won't know about this one.
Yeah, this one's really old. No, so it's great for doing buses, particularly serial buses.
Yeah.
Parallel buses, it tends to break down a little bit, and the major reason is that they don't support a separate clock line. So something that a traditional logic analyzer can do is what's called state analysis, and the idea is that you provide not just data lines but a clock line, and that clock line will latch the state of all the other pins every time it hits an edge.
So you don't have to oversample.
And this is great because it uses a lot less memory as well. So it's much easier to analyze the data that results from that.
Yeah.
And so if you've got something that's a more traditional application for a logic analyzer, having that clock is fantastic. But even with a modern setup, for example, if I could just go in and select state mode and then hook it up to a SPI bus, I wouldn't have a gigantic mountain of like 10 gigs of data to go and sort
It's
through.
amazing how fast it goes.
A few hundred K.
Yeah.
I know. It eats
you're
your
like,
RAM
what the hell?
alive.
I don't even think I have a hard drive that can do this.
And for digital, they're only sending the transitions. So it's extremely compressed already.
Yeah, don't do analog. That's all I'm saying. You will be sad. Your computer will be sad.
Analog is tricky. Although I have a little scope probe adapter that I made for it, so that you can use it with a regular oscilloscope probe, and it's compensated as well. So it's basically a resistor. Was it a resistor in series? I think it's a resistor in series because the Salier's got like I want to say it's 500K input impedance. I don't remember offhand. But anyway, I stuck a resistor in there, hook it up to an oscilloscope probe, and it works. And it's compensated. So if I hook it up to a square wave generator, I actually get a square wave. I don't get something that's got these little peaks or troughs or anything funky like that. So that's also useful. I would say the other tool that I am getting better at, which I wish I were better at, but it's just going to take practice. That is Ghidra. And so Ghidra, of course, is the reverse engineering tool that the NSA made, which they released to the world. I wonder if it has spyware in it.
I feel like
surely it would have been found by now.
Yeah, is it spyware if a spy agency made it, even if it doesn't call home?
I don't know.
I don't know.
Exactly. But I felt like because they like gave the source code out, and it's been now a couple years. I understood it like the first couple years.
I feel people would have found something if there was something
by now.
Yeah.
Well, I think the joke's on us because the exploit's probably in the Java interpreter.
Well,
I'm sure some clever person could figure that out.
Yeah.
So anyway, Ghidra's been nice. It's really helpful. I used the free version of IDA a little bit, and I had a really hard time understanding how to drive it. I tried. I'm not sure how you pronounce it. It's like radar or something like that, and it was also really difficult to use.
Yeah,
but I found that Ghidra is.
Yeah, we interviewed they forked it and did a GUI for it now, and we had them like 5 episodes ago or something. I think.
Something like that. Okay. Yeah, Cutter.
Yeah, they're actually using the Ghidra decompilers because they're open source. Yeah, and they're all C++.
That's great. Yeah, so I found that to be very useful for all the stuff that I've been doing with reverse engineering PC BIOSes and pretty much any reverse engineering task that has to do with code is something that Ghidra is very handy for. And then the third tool is maybe a little non-traditional, kind of old school, but I think it's going to make a comeback, and it is your own brain. Or in this case, my own brain.
Wait.
Where can I buy one of these?
Wait, I want to know, like, this, what I've learned in the last 10 years is, I've basically been outsourcing like how to figure out what I'm going to wear every day. I've been figuring out how I'm going to like feed myself. I've outsourced that to Soylent. I don't do shopping anymore. Someone else takes care of that for me. It's all auto subbed. And I heard I don't have to wash my legs. Like, I found that out on Twitter.
So your brain, how do you?
Yes. How does that work? Tell us more.
So the best part about your brain is that you come with one. Everyone listening, you already have a brain.
What?
It's there. And there's some effective ways you can use it. But because every brain is different, it's up to you to learn how to use yours effectively. One of the things that's really weird.
Yes. Does it have security features on it?
Yes. No one else can hear your thoughts. unless you speak them
That's
out loud.
probably a good thing.
I hope it stays that way.
Yeah.
I wonder if he understood that.
Oh, no, that's not right. Anyway, so I use it as a troubleshooting tool. And one of the things that I'll do is like, say I'm doing some reverse engineering task. What you want to do is try and set up a framework for questions. And so if you have a physical thing in front of you or a virtual thing in front of you in the computer, you have a goal in mind and you need to figure out how to get from where you are now to that goal. And so what you kind of have to do is it's like cracking a nut. Like you do it you kind of squeeze it. You go through a little bit at a time. You're trying to break into this thing. You're chipping away at the problem. You're trying to figure out, well, I'm trying to get from A to B, but I need to take one small step first. What's that first step going to be?
Yeah.
And then to get from that step to the next one, you got to ask yourself a series of questions. Like, for example, I'm trying to repair a 8086 accelerator card for an old computer, like an IBM 5150, original IBM PC. And the card itself, it's an interesting problem to solve. And it almost doesn't matter that it's out of date because the processes, the way that I use my brain to approach the problem is the same way that I use it to approach other problems. So I plug it in, I turn on the computer, and nothing happens. So the question is, what next? What do I do next? So I ask myself a series of questions. Well, nothing happens. Why does nothing happen? Normally, something does happen. Normally, the cursor will start blinking on the screen, except in this case, the cursor doesn't blink. So then I ask, well, why doesn't the cursor come up? Why isn't the cursor blinking? Well, because something is not initializing the registers in the video card that make the cursor come up. Oh, okay. So that means that I'm probably not running any code right now. Okay, well, how can I prove that? How else can I prove that? Maybe I can put an oscilloscope on some chip select lines for, say, the ROM chip and see if the ROM chip is ever getting selected or see if there's any activity there. So the idea is that there's this back and forth. I do a little experiment and then I think about it. So I let my brain kind of work on it. And it's not always something that I'll do consciously, right? So I won't always be asking myself those questions like, well, this is happening. Why is that happening? Sometimes, you're tired. It's the end of the day. You've already been at work all day and now you're working on a side project. It's like, you know what? I'm just going to go play a game for a while. Or maybe I'll just go and sleep. And then when I wake up, I'll get this little burst of inspiration that'll just sort of pop into my head. And that's your subconscious, right? So your subconscious will continue working on these problems even when you're sleeping or doing something else. And so sometimes what you have to do with a project is just set it aside for a while and then let your subconscious think about it and then come up with some new ways to approach the problem. Or if you're doing another activity, that other activity might give you inspiration, things to try that will help you solve that other problem. So one of the reasons why I have multiple projects going on almost all the time is that occasionally the projects will cross-pollinate and I'll get ideas about how to solve one problem based on another problem on another project that I'm trying to solve. And so these are all different tools that I've developed over the years for trying to use the power of my brain to solve problems.
The power of the brain.
And the best part is that you get better at it with practice.
Yeah. I think that's the one thing that I think a lot of people don't realize until maybe it's too much later, probably. Not necessarily it's too late.
Until it's too late.
It's never too late.
Yeah. Is that you see people like they had this brilliant discovery. It wasn't like it's almost impossible for it to just suddenly happen. People were practicing. They were working their way up to this. They developed an expertise. They, have this problem solving methodology that they're applying that's well practiced and well vetted with themselves. People think that it's like, like watching an episode of Scooby-Doo, like, oh, suddenly like, oh, well, here it is. This is how it's all solved. No, it just takes a lot of practice and failures.
Yes, these things don't spring into your head just all of a sudden. I mean, of course, I wanted to use the example of Edison and the light bulb, but of course he didn't invent it. But his ideas for similar products didn't just suddenly pop into his head, right? And that same goes for other inventors too. I mean, these were all things that they focused on and they studied in great detail, right? So maybe they found a particularly interesting problem and they just doggedly pursued it down to the end. Like there's a sort of lesser known engineer named Herta Ayrton, and she was essentially the discoverer of negative resistance. And you can go and look her up. There's some really interesting stuff that she wrote. And it all kind of started when she was looking at an electric arc lamp, because in the 19th century, when you didn't have an incandescent light bulb, you would use an arc lamp instead. And she asked a very simple question: why do they hiss? So an arc lamp is basically two carbon rods with a spark going in between them, and it makes that sort of buzzing and zapping sound. And her question was, well, why? And then using essentially 19th century equipment, like she didn't have an oscilloscope or anything like that, basically no test equipment, she was able to discover that arc lamps actually oscillate because they have a resistance, and there's a particular region of the VI curve when you go and you measure an arc lamp, and that particular region has a curve that sort of folds back on itself a little bit. Basically, the slope goes negative, and you get a region of negative resistance. And because it's negative resistive, it creates a oscillation just in that particular region. So any parasitic inductances or capacitances plus a negative resistance, you essentially automatically get an oscillator. And she discovered this all in the 19th century, and nobody else had up until that point. In fact, they didn't even believe that negative resistance was possible until she proved it. And so it took a few years of study for her to figure it out. And then she goes and publishes this classic paper. And so, of course, it didn't spring fully formed from her brain. She didn't just wake up one day and say, oh, I know what's going on. It took a lot of work and a lot of study and a lot of dead ends.
Yeah. Nice. Thank you so much for that story. That's a really nice way to, really nice note to end on.
Better note than some of the earlier conversations.
Okay. Well, thank you, Tube Time / Eric, for joining us. Wow, I couldn't think of a more wooden way to say that. Maybe we should get that. Is there anything that you want to plug besides your brain?
Well, I wanted to say I really appreciate y'all having me on. I had a really great time talking with everybody, and I hope people appreciate listening to it. You can actually find me on Twitter. My handle is at TubeTimeUS. And my DMs are also open, so you can send me messages, and hopefully I'll get the time to answer it. It won't always be right away because, as you imagine, I do get quite a few messages. But if I can, I'll try to answer it if you've got questions about anything. And I've also got a blog at tubetime.us, and that also includes sort of a best of collection of links to my Twitter, because Twitter search is terrible. So don't use that. Go to tubetime.us, and then you'll see the list, and you can go through and browse whatever threads you think look interesting.
Oh, wow. I hadn't seen the Tube Time best of. Yeah, this is excellent stuff.
Alvaro.
It's got all the things.
Yeah, all the things.
You can find me on Twitter at Alvaro Prieto. It's just my name. alvarop.com. That's it. Yeah.
Okay. You can find...
Jen?
You can find me probably on Twitter. At this point, I have way too many Twitter accounts for different aspects of my life. But the one that the audience may or may not care about is at RebelBotJen. You can find me there. I might be slow on the DMs because they're not totally open. But you want some DMs that you can slide into because you have comments or suggestions, or you just want you want to tell us about what you think about this episode, last episode, your friend Bob that's been doing some interesting things and you don't get it. You can tell us all about it in the DMs at unnamed_show, or hit us up at the comment form that we never look at.
We still have one.
But we still have one.
It goes to a spreadsheet somewhere.
But you can also still find us if neither one of those work for you, because you don't have a Twitter account and you don't understand how comment forms work. You can still find us by going to unnamedre.com. Let's see what else. We have a Patreon. I love our Patreon supporters. It's amazing how many people talk on that Discord that we have just for signing up, including our past guests. Let's see what else. Oh, feel free to review our podcast using your favorite podcast app, whether it's iTunes, Stitcher, Spotify, Amazon. I don't know. Are there other ones that?
No idea.
I have no idea. Anyway,
Probably.
probably. We don't know all the stuff. Tell us. Oh, we're probably on Google something. Anyway, that's pretty much it about the show. Was there anything else that we needed to do? Can we go?
I think we covered everything.
Okay.
This is a new record, by the way. Jerry has lost now. You've beat Jerry's record.
Make sure you tell. Yeah.
I feel so special.
Should we break this one up? I have no idea.
Hell no.
Okay.
I figure you're going to edit it down to something really short, but maybe not.
What was there to edit out? What
offensive stuff?
We didn't spoil any movies for anybody. We have to put in some sound effects.
Yeah, so we're gonna make.
What about that one? What about that one Harry Potter spoiler?
Oh my god! Yeah, maybe we.
Yeah,
should
we don't talk about that one.
Oh man. Okay, maybe you got me on that, but I do want to give the final tallies. There were 2 puns this episode, which is kind of low.
That's extremely low. Yeah,
that's a pun per hour.
You were extremely controlled. I'm surprised. I was ready for more, but
I guess we'll find out if we can work a pun into the title for this one.
We'll figure something out. Awesome. Okay. Again, thank you so much for joining us.
Thank you guys. Till next time. Thank you. Thank you too.
Thank you. And on this show, we're going to have Tube Time, and we're going to talk about television, of course.